Today's topic is based on quite a number of papers by now, with also quite a number of collaborators. So I have a slide just for them. And yes, so what's this about? As you know, strongly coupled physics is a kind of an unsolved problem. Still, it's very difficult to access because we don't have a small parameter in which we could do a perturbative expansion. So what do we do in this case? In general, we try to make use of the symmetries of our system as much as we can, or we look at special limits or subsectors of the theory where things simplify nonetheless. And that's also what I want to do today. And I will study theories which have some kind of global symmetry group. If I have a global symmetry group, I can decompose the Hilbert space into sectors of fixed charge under the action of this global symmetry group. And I will do that. I will fix a charge, and in particular, I will focus on subsectors where this charge is very large. And we will see that this large charge will become a controlling parameter. So I can go back to doing perturbative expansions. That's also why my title is large charge expansion. So we will see that this expansion, how this comes about. I will be mostly talking about conformal field theories here. And obviously they play an important role in theoretical physics. First of all, they show up at the fixed points of the RG flows. They describe critical phenomena from a quant math side. And they're even related to quantum gravity via the ADS-CFT correspondence, and also the worldsheet theory of the string is described by a CFT. However, in general, CFTs, they don't have, clearly being conformal and scale invariant, they do not have any intrinsic scales. And by naturalness, they have couplings of order 1. So we do not have any small parameters in general available. Of course, there's a number of things we can do anyway in 2 dimensions. There's lots of stuff known analytically to work with. Then in more than 2 dimensions, you can use, for example, the conformal bootstrap, but this talk is not about that. You can work directly on the lattice, or you can use some non-perturbative methods, but on the whole, they're really a prime candidate for the large charge approach. And they have the other practical advantage that they have all this extra space-time symmetry that we can use to constrain the terms that can appear in the linear sigma model or the nonlinear sigma model. So I'll be focusing on CFTs, even though in principle, there's, apart from practical reasons, there's no in principle reason why I shouldn't be able to use this approach also in other quantum field theories. So let me give you a quick overview. This was my introduction. I will be focusing as the simplest model on the O2 model, where I'll show, first of all, the semi-classical treatment for finding the ground state. Then I look at the fluctuations, and I'll give my result and compare also to lattice data. And then I want to generalize this a little bit, and the most obvious generalization of the O2 model is the O2n vector model, where I follow more or less the same course as in the O2 model. I give the EFT calculation, and then I will, for the last few minutes, depart a bit from the EFT topic and talk about the large n limit that we can take here, where we can do calculation not in the EFT, and we can even use some resurgence methods here. And I'll end with a largish summary and a bit of outlook. So let's get started. Let's look at the O2 model. I want to look at the O2 model in 2 + 1 dimensions. And in the ultraviolet, it's simply given by this Lagrangian. We have a complex scalar field and a 5⁴ type coupling. But here we are interested in EFTs, right? So we will forget this UV thing right away, because we know this model flows to the Wilson-Fisher fixed point in the infrared. And I assume that in the infrared, I still have a complex scalar field, which I want to encode for my future convenience like this, with the radial mode and an angular mode chi. In this form here, also the global U1 or O2 symmetry of the system is manifest. It's simply a shift of the field chi. So I will put this system on a compact manifold. I'll be in particular interested in the two-sphere because I want to use later on the state operator correspondence of conformal field theory. But yeah, you can also put it on a torus or anything with some scale R. And since I'll be fixing the charge, I will have a second scale in my theory, given by this charge Q, or by the charge density, if you like. So the range where I will be studying this CFT is in between 1 over R and square root of Q over R, where here G is the UV scale, lambda is the cutoff of my EFT. And now I want to write, for starters, a Wilsonian action. I'll write a linear sigma model for this IR theory. And I'll make an assumption, which I'll be justifying shortly, namely that the radial field, the radial mode A, has a large VEV. So I start by the kinetic term for A. And from this, I can read off directly that since I'm in 3 dimension, A must have dimension 1/2. I feel 1, 2, and 3 from the 2 A's. So I must have a to the 6th term in the potential. Then I also have the kinetic term for chi, and I have here the conformal coupling term where I couple to the scalar curvature of the manifold that I'll be working on. So on the sphere, I'll just put in the value for the sphere here. I have 2-dimensional constants in here, the B and the lambda. These are Wilsonian couplings, so I know nothing about these. So this is my starting point for my calculation. That's my linear sigma model in the infrared. And this was constructed such that this is scale invariant here at this level. Now I want to just do a simple semi-classical analysis to find the ground state. So I will solve the equations of motion from this Lagrangian at fixed Noether charge. And here in this case where we have just a complex scalar field, we know that the solution must be homogeneous in space because we don't have enough degrees of freedom to account for more Goldstone bosons that would arise if we also broke some spatial symmetries here. So I can write the charge density in terms of B, A, and chi dot. And the lowest energy solution we find is given by A being constant, having some VEV V, and chi having a non-constant VEV mu T, where mu is here expressed again in terms of the charge density B and the VEV of A. Now to find the lowest energy solution, I have to minimize the classical potential. I have to determine this VEV V here. And the potential here has these 2 terms we've seen before, where we had the A square and A to the 6th term. And now we also got this centrifugal type term. So the potential, the classical potential looks like this. So we see directly that the minimum is not in 0 here, but somewhere away from 0 because of this centrifugal barrier that we have here. And if we minimize, we see that this VEV V goes like Q to the 1/4. So if we fix Q to be very large, then this assumption that we made that A has a large VEV was justified. The mu, if we put everything back here, scales like square root of rho, square root of the charge density. Now we can just do a Legendre transform and get the energy of the classical ground state at fixed charge. So this is clear, it's not the vacuum of the full theory, but the vacuum in this sector that we look at with the fixed charge Q. And here this depends on what manifold we are compactifying on. I still have 2-dimensional parameters that are related to the B and lambda of the before. And here, this is the volume of the manifold and the curvature. So we have this dependence on the compactification manifold. So if you have a flat manifold, this term will be gone, for example. And the leading Q scaling is in Q to the 3/2. Then we have this Q to the 1/2 term, and everything else will be suppressed by negative powers of Q. So if Q is very large, this is going to be very suppressed. Now this becomes my vacuum, and I want to look at the fluctuations around this vacuum. So now we're ready to tackle the quantum story. And we want to parameterize the fluctuations on top of this vacuum as a VEV plus fluctuations A and mu T plus some fluctuation chi hat that we normalize with V. And it turns out then that this fluctuation is actually a massive mode. So if we're just interested in the low energy spectrum, we can get rid of that one. Chi, on the other hand, will turn out to be a Goldstone mode related to the symmetry breaking that is taking place, so the spontaneous symmetry breaking of my ground state. So how does this, what's the symmetry breaking pattern like? We started with the conformal group times the global symmetry. And in the first step, from which we only get massive Goldstones, if you like, we see that the space-time symmetries are broken. The boosts are broken in particular. These are the time translations. And then in the spontaneous step that will give us a massless Goldstone boson, the internal symmetry is broken, that we have only a D prime left, the helical symmetry, which is made of the D and mu times the generator of the O2 or U1. So from this, we expect to have one Goldstone, which is this chi of before. So now we're ready to get rid of A. In part, as we can't actually easily integrate it out, but for the leading order, we can just use the equations of motion to eliminate A. And the leading order nonlinear sigma model action is given by this expression here, del mu chi to the 3/2 with some Wilsonian coefficient in front. Now this we could have actually guessed purely by dimensional arguments already. Chi is a phase, so it's dimensionless. So we have here dimension 2 and we want to get up to dimension 3 here, right? So this is our leading order. But we're not satisfied with that. We want to figure out what other terms can appear here, and the different ways of doing this. You can do the coset construction, or you can just use, first of all, dimensional analysis. We impose parity and scale invariance to see what other operators can appear. Of course, we would have infinitely many of these, but now we use the scaling with mu or q to figure out which of them will be suppressed. So we only keep those operators here that are not suppressed by inverse powers of the large charge. So we use the Ross scaling, and we remember that on the ground state, chi goes like mu t. So del chi will go like rho to the 1/2, and higher derivatives of chi already have a negative scaling, rho to the -1/4. So the highest order that can appear is that term we've seen before. That's short for the del mu chi to the 3/2. That was the leading order Lagrangian. And at the sub-leading order, we get a term R del mu chi to the 1/2, which by itself is a scale invariant term, but it's not fully conformally invariant. It's not invariant under special conformal transformations, but we can make an invariant, a fully conformally invariant combination here. However, this second term we added has a negative row scaling, so it's not actually going to appear to the order that we're keeping terms in our effective action. And it turns out that this is everything. These two terms are the only terms that do not have a negative row scaling. So to write this again, the result for the nonlinear sigma model action is this thing here. where we have, again, two-dimensional parameters in front, and we have these two terms, and everything else is suppressed by inverse powers of Q. So we don't really need to keep track of a lot of terms here in 3 dimensions. If you go to higher dimension, there are more couplings to geometrical invariance that can appear. So there will be more terms appearing, but here in 3 dimensions, this is a very simple expression. Now, of course, this has these funny fractional powers here and looks a little bit irregular, but here we must remember that what we put in here, this chi, is always the ground state chi mu t plus chi hat. So this, in truth, should be understood as an expansion around the classical ground state. So let me do that. I expand to second order in the fields. So I have here big constant contributions from the ground state itself, and then I have this bit here that comes from the Goldstone. And from here, I can read off the inverse propagator and get the dispersion relation. And we find that chi hat has the dispersion relation that goes like p over square root of 2. So indeed, it acts like a normal Goldstone. And the square root of 2 here is actually model invariant. This comes just from the fact that this is conformal invariant. In general dimensions, this goes like 1 over square root of d and comes from the tracelessness of the energy momentum tensor. So indeed, as we expected, the chi is a relativistic Goldstone. So we see the fact that we fix the charge and we didn't even need the large charge at this point. This has allowed us to write now the nonlinear sigma model in terms of this Goldstone. This has given us a light degree of freedom to write our action in that we didn't have before. So even if we start from something strongly coupled, we have now this chi in terms of which to write the action. So we've seen already at tree level that we only had these two terms that we needed to take care of. What about the quantum fluctuations? Are the effects also controlled? And here it turns out that the only effect that is not suppressed by a negative row scaling is the Casimir energy, the 0-point energy of chi. And this I can evaluate with the Coleman-Weinberg formula. So this is the usual story we use here, zeta function renormalization, and we find it goes like q to the 0, so it doesn't have a positive q scaling either, and the numerical value is this minus 0.09, etc. Now that we have the action, let's actually go and calculate something, right? Let's calculate observables, which means in CFTs, what we need to do is to calculate the so-called conformal data, meaning scaling dimensions of the operators and 3-point function coefficient. From these, we can construct, in principle, all the endpoint functions. So let's start with the conformal dimensions. And to get those, I want to use the state operator correspondence of CFT that relates the operator dimension of operators inserted here in the plane in R to the D with the energy of a state in R to the S D minus 1. So here in 3 dimensions, we're on the 2-sphere here. And just before, I have already calculated the energy of the ground state on R times S2. And this gives me directly the scaling dimension, thanks to the correspondence of the lowest operator that carries this large charge Q. So this operator dimension is given by R0, where R0 is the radius of my 2-sphere. The ground state energy, which is made up of the classical ground state energy and the Casimir energy. And that's the result that we get. So we have here the leading term with scaling with q to the 3/2, then q to the 1/2, the Casimir energy, and everything else is suppressed. So yeah. So I can summarize the EFT at large charge in this very simple formula that I get a big contribution from the classical vacuum, I get contribution from the goldstones, and everything else will be suppressed by negative powers of Q. So let's test this prediction. In general, it's not so easy to make sure if your strong coupling predictions are correct, because there are very few things to test against. But so this was our result for the scaling dimension. Then one of my collaborators actually got in touch with lattice theorists and got them to calculate this on the lattice completely independently. They managed to go up to charge 11, which is maybe not a very large charge, but this was the state of the art that could be done on the lattice. And what you see on this plot is the result. These are the Monte Carlo data points. These horizontal lines are actually error bars that are so small that, yeah, they basically collapse onto each other. And this line here is this curve here. And they did a 2-parameter fit on these C3 halves and C1 halves. And you see this works extremely well. And they got numerical values out for these coefficients here. And what is kind of unexpected and surprising is that this works really well down to charge 1, which is by no means a large charge, right? I mean, we wouldn't have claimed that this would have worked down to such small charges, but there it is. That's what they found. So for O2, this seems to have worked really well. So the natural question is, was this by chance? Is that going to work in general, right? So where else is this large charge expansion going to work? So one clearly can just go to other known CFTs and try out if that works, or assume that a certain CFT exists. And the most obvious generalization where we are in 3D is to go to the O2N vector model, where now we have a non-abelian global symmetry. And the fact that we have this non-abelian symmetry will lead to new effects. That's actually quite interesting. Then we also looked at matrix models, SUN matrix models. There aren't so many examples of bosonic CFTs in 4 dimensions, but there was one example that actually has a UV fixed point in 4D that we tried out. And then there's this whole class that the more formal community is interested in of superconformal field theories. And also here, the large charge expansion works, but it turns out that if you have a moduli space of vacua, so if you have not just a single discrete vacuum like here, but a space like a line of vacua, things work very differently. And it also works quite well in so-called non-relativistic CFTs, which don't, these are non-relativistic systems that don't actually have conformal symmetry, but Schrödinger symmetry. But here we can use the same technique. These symmetries are enough to constrain the terms appearing in the sigma models, that we can do the same thing. It's a bit more nasty doing the state operator correspondence, because there you have to confine the system into a harmonic potential, which makes everything space dependent. So it's more nasty, but it still works. But today in this talk, there was another point, so I can go slightly away from the conformal point or the Schrödinger point to see if things still work out. And in fact, this is also doable. But as I was going to say, today I'm just going to focus here on the O2N vector model. Let's move on to the O2N vector model, which is really an obvious generalization. Instead of just this complex scalar, we have now a vector with 2n entries here. And as before, we have the kinetic term, then we have the coupling to the curvature, and we have this phi to the 6th type term in the linear sigma model. But one thing we just need to keep in mind here is that now the conserved current itself is already matrix valued and transforms under the global symmetry group. So that's what the conserved current looks like, the Noether current. And also the charge is now matrix valued, and I can decompose it on the generators of the symmetry algebra. So I can write this as this sum over the coefficients QA, TA, where the only things we can fix are the coefficients of the Cartan generators because they are mutually commuting. So in practice, when I say fix the charge, I will be fixing these QA coefficients here. Now I will introduce complex coordinates. So I will form complex fields out of these real fields. I have n complex fields made out of these 2n real fields. And then I would just do the very same thing that I've done before. I find again the classical ground state via the equations of motion at fixed charge, where here it's not anymore automatic that the solution will be homogeneous. We have more room in our symmetry group, so there can be inhomogeneous configurations. But I will make the answers that it's homogeneous, and if I find such a solution, it will be the lowest energy solution. And indeed, I find solutions of this form here where we have here these A's in the radial directions times e to the I mu t, where we find this is really the solution is not an input, that we have only one mu. So we don't get different mu's for each of these components, but one mu for all of those. And here, this v square is given in terms of these A's, and the mu square is given in terms of the potential. And we have an explicit breaking from O to N down to UN. And now we can do a neat trick that we do a basis transformation for the generators, in which the ground state can be brought to this form here, that we only have a VEF in this first direction, or well, whatever direction you choose, and no VEF here. And also the charge matrix then takes a particularly simple form, that we only have a block here that is non-zero, and these Q's here are the sums of the Qi's here. And when you now inspect the form of this vacuum, you see that the symmetry breaking pattern is that the UN goes down to UN minus 1, because you have here these n minus 1 components that you can transform freely still. And we see that any homogeneous state of minimal energy with a fixed total charge Q, they're related by these transformations and have also the same energies. On the other hand, what happens if I instead look at the configuration where I have n different mu's at different chemical potentials, that then clearly I cannot just rotate into this configuration here. Then the thing that has to give way is the assumption that it's a homogeneous state. So such a state must be inhomogeneous, which is also something we studied, but I will not be talking about this today. Now, as before, we go to the quantum description. So we want to look at the fluctuations around the ground state, which I now here parameterize by a complex fluctuation pi. And I do the same thing. I expand the action around the ground state to quadratic order in the pi's. But if I use this rotated basis, where the ground state has this form here, something very neat happens, namely that the first field here completely decouples from the others. And the first bit, it's now in a different notation, but this is the exact same thing as we had in the O2 sector. Here, these covariant derivatives contain the mu's in here. So this is the sector we had before. So all the O2N vector models have this O2 sector, and we have a second new sector with the pi i's where I is not 0 here. And this new sector we find now contains n minus 1 massive modes with the mass of 2 mu, and paired with n minus 1 massless fields. And the dispersion relation looks now a little bit different. It doesn't go like p, but with p square over 2 mu. So all in all, we have the universal sector, where we have this goldstone we've seen before with the linear dispersion relation. And then we have this new sector with n-1 massless modes with the quadratic dispersion relation paired with n-1 massive modes. And this is actually something that is known in the literature. These are so-called non-relativistic or type 2 goldstones, which were, for example, discussed by these authors here already. The symmetry breaking pattern, in this case, we've seen again in 2 steps. We have conformal group times global symmetry. The boosts are broken, and here we break down to UN. And then we have this spontaneous breaking from UN down to UN-1. So in total, we expect as many goldstone modes as is the dimension of this coset UN over UN-1. So n-1 of them. So let's just verify this count. We have 1 type 1 goldstone mode and n-1 of the type 2s, which need to be counted double. And this works exactly out to this formula here. So the count is correct. Now, before we've seen that we got a contribution from the 0-point energy of the goldstones, but it turns out the only thing that again contributes is this relativistic goldstone here, because the energy of the type 2 goldstone bosons is subleading. So this comes at a later order. So if I write the formula for the anomalous dimension as before, it looks exactly the same. So there would be at later orders other contributions here. But if I only keep the non-negative orders in Q, I get the same type of formula, but these coefficients here, the C3 halves and C1 half, they depend on what n we've chosen here. So these are n dependent. On the other hand, this one that comes from this O2 sector that is present in any O2n model is completely universal and was also verified independently in a numerical calculation by De La Fuente. So again, to make sure that things were still working out, also in the non-abelian case, we went back to our lattice friends and they modeled the simplest non-trivial case of these non-abelian models, which is the O4 model, and that's the result here. You see again, this is the curve we predicted. This is their Monte Carlo data. So again, this works extremely well. And doing the fit, we get now somewhat different values for these coefficients, C3 halves and C2 half, since they are independent. Good, so now for the last few minutes of my talk, I allow myself to depart a moment from the EFT theme, because in the O2n model, we can actually take the large n limit now, where Q needs to be still bigger than n. So we have very big Q and big N. And here we don't actually need the EFT at all that I've been discussing so far, but we can just do the saddle point in the path integral. And what we find in leading order in N is that, the theory is solvable and we get the same powers of Q in the scaling dimension. So we can verify the EFT results that we had. If we want to reproduce the dispersion relations of the goldstones, the type 1 and type 2, we can also do that, but we need to go to the next to leading order in N. But since we now have an extra control parameter that we didn't have before, we can actually do a little bit more and we can go beyond verifying the EFT results. And one thing that we can do in large N that we couldn't do within the EFT is to find these coefficients, C3 halves, C1 halves, etc. To leading order in N, they look like this. So we see that they go inversely here. This one goes like square root of 1 over n, whereas C1 half goes like square root of n. And on the lattice, for the O4 data that we have, this here is actually still within 10% of the lattice measurement. So this is what you get from this formula for n equals, well, actually, yeah, it should be n equals 2 because it's 2n here. So you see, this still works out fairly well, seeing that 04 is not large n at all, right? And our friends even put in some more work. This is some to date unpublished lattice data where they went to higher n's here for C3 halves. You see, the higher the n goes, the better this this starts to fit with our prediction here. The C1 half is a bit more difficult, but yeah, it's still, this is not large n, right? So this looks at least plausible that the lattice data is corroborating this large n result here. We can also do something else that we couldn't do in the EFT. We can take a small charge limit where now Q over N is supposed to be very small. And in this limit, we can first of all identify that the operator whose dimension we've been calculating is simply phi to the Q. And the scaling dimension is, as expected, if we divide here by Q, the delta goes linearly in Q, where here we find directly the engineering dimension of phi. And this here comes from the tree level, and from the one loop calculation, we get the next order here. So this is what we would expect in the small charge limit. But yeah, we've seen at large charge, this works completely differently. This was verified by a loop calculation, which wasn't published, but has been verified by Sergio Benvenuti. Now we can even try to do more. Namely, we can try to interpolate between the large Q and the small q limits in the O2N vector model using resurgence. And I will just summarize this very briefly because that would be an entirely different talk. So first of all, one thing we see is that this large charge expansion is an asymptotic series where the coefficients diverge as 2n factorial. An asymptotic series has an optimal truncation, after which adding terms makes it actually worse again. And this is at order squared of Q. And this actually helps explain why we've seen in the lattice that the comparison worked so well for really small charges, because the smaller the charges, the fewer terms we need to take into account in the expansion here. We can even get the non-perturbative corrections to the expansion, which go like e to the minus 2 pi k square q over 2n. And comparing the result for the scaling dimension in the small q expansion and the resurgence result numerically works out at least to 10 digits. We didn't try any more because adding another digit would have added like a week of computation time. So we left it at 10 here. Yeah, that's the result of our latest paper here. So let me start summarizing here. So today we've seen that what we've done was studying different CFTs in sectors of large global charge. And we've seen concrete examples where we had a strongly coupled fixed point, which really simplified strongly in a special sector, namely in a large charge. And we've seen the O2N model today in 3 dimensions, where we could calculate the scaling dimension of the lowest operator of charge Q. And we found this formula here, where we've seen the C3 halves, they are n-dependent. The Q scaling is what it is, right? It doesn't change. And then we have this universal contribution from the conformal Goldstone, from the Casimir energy. At least in the cases that we have lattice comparisons to O2 and O4, we have excellent agreement. So this evidently seems to be true. If we now also go to large n, we can work with the path integral, where we have more control than in the EFT. This was all done in the EFT. And we see we could even take the small charge limit and do some resurgence calculation. But of course, so today that's what I was talking about, but this large charge approach can be applied beyond the vector model and, for example, in matrix models or superconformal field theories. Now there's some questions that maybe you have had in the course of my talk. So one thing is, does it actually work? And for all the examples where we tried it, it has always worked. And as I said, we have lattice confirmation in these particular cases. It works for CFTs and superconformal field theories, as well as non-relativistic CFTs, but in principle, there's no reason why it shouldn't work in general QFTs, even though the actual EFT calculations will be harder without the extra spacetime symmetry. And for the spacetime dimensions, it quite obviously works if we have more than one space dimension, since we need goldstones, right? But new work actually indicates it also works for in 1+1 dimensions. Now, does it matter what kind of global symmetries we use? We've checked these types of symmetries and yeah, they all worked. So if you have a different interesting model with a different global symmetry, yeah, one should try. If we pick several charges, so if we have a non-abelian symmetry, there are two cases. If they have the same chemical potential, we find homogeneous ground state solutions where we have now two types of Goldstone bosons. On the other hand, if we have different chemical potentials, these solutions must be inhomogeneous in space. And what we can learn from this approach is that we can actually calculate CFD data and thus endpoint functions of strongly coupled CFDs. I've only showed the scaling dimensions today, but the group of Ratazzi et al. In Lausanne, they have also calculated 3-point functions. Now there's quite a number of further directions. One could look at supersymmetric models, especially in the case of higher dimensional moduli spaces. This hasn't been done yet. Then I mentioned briefly the ADS-CFT correspondence earlier on. So we have now a CFT at fixed charge. Would be interesting to study the gravity duals to see what we can learn from this. There have been some attempts, but really there's much more to be done here. Then people have also started studying operators with spin. So far, we just looked at the lowest scalar of a certain charge. This has been studied by these people in Lausanne already. And it would be interesting to also make a connection to the large spin results, which are out there. It might also be interesting to study dualities at large charge, because especially if you have a strong weak duality here, we have a certain degree of control over the strongly coupled side. So this may give us a handle for checking dualities that are conjectured, for example. There's been already some comparison to Bootstrap, which where they were able to get the same type of results, but not much has been done. Of course, it would be interesting to see more lattice simulations to compare, for example, the results for the inhomogeneous sectors or more general ON models. One could also study CFTs in other dimensions. Interesting ones would be 2, 5, and 6, for example, that haven't been done yet. Then people have started looking at Chern-Simons matter theories at large charge. Then there has also been a number of papers where people have looked at the 4-epsilon expansion, which also gives you another extra control parameter, similarly to the large N case. So people can do perturbative computations in this case. Then yeah, 4D CFTs would also be interesting if there was an IR fixed point to look at. And then there's the whole issue of, can we go away from the conformal point and will this still work? Then there are also some funny non-unitary CFTs, like fishnet CFTs, for example, where it might be interesting to study. also at large charge. And finally, there's the whole category of fermionic theories. And if we can treat those at large charge, we could, for example, try to use it really for QCD, for example, at large baryon number or large density. And there has been a little bit of work here by these people, but also there's much more to be done. And yeah, with this, I'm finished. So thank you for your attention, and I'm happy to take questions.